All right, please take your seats. We are going to start the afternoon session. We have a switch of topic. So the speakers will be talking about supernovae. And the first speaker is Martin Obergaulinger. And he will tell us about magnetic field amplification during the core collapse.
Thank you very much. It is a great pleasure to be here to talk to you a bit about some recent results we obtained for the amplification of magnetic fields during core collapse. So as just mentioned, the stage now is a bit changed. We are now going to the very dynamic phases of the formation of a proton-neutron star during the collapse of the core of a massive star. But before everything else, I'd like to thank my collaborators at the MPA in Garching, Ewald Müller, Thomas Janke, and Jérôme Guillet, who is just now moving to Paris, and at Ricken, Oliver Just, and our group in Valencia. We are now going to focus in this and all the talks afterwards on the supernova, the core collapse leading to the formation of a proton-neutron star, and possibly the expulsion of a lot of mass at high energies during a supernova, or perhaps even a gamma-ray burst-related supernova. So, but the mechanisms for producing a successful supernova are going to be the topic of the next talk by Christian Ott, so I won't go into the details here, but just mention that we have a few reasons to believe that in some of them, magnetic fields are at least superficially important. I've listed a few of them here in ascending order of plausibility. First of all, we can of course say, even if we don't see fields in the supernova ejector, they may nevertheless be present in the proton-neutron star and play a certain role during the explosion. But that's basically a weak excuse. The next ones are a bit better. Some explosions have a bipolar geometry, which can be explained by non-magnetic effects very well, but magnetic fields are very good at producing such bipolar geometries. The same is true for pulsar kicks. Magnetic fields, plus in particular if rotation is present, may produce them very well. And in Sergei's talk at the end of this session, we'll also see that they have been invoked for explaining very highly energetic supernovae. But of course, for example, the ones related to gamma-ray bursts and for example, here, as you see in these plots taken from a picture by Metzger a few years ago, where the luminosity of gamma-ray bursts may be explained by the action of a very strongly magnetized proton-neutron star in the center of the explosion. But of course, the best evidence for the presence of magnetic fields in core collapse and proton-neutron stars are the magnetic fields of neutron stars, which are produced in core collapse and supernova explosions. Probably don't have to explain a lot about this diagram, but the most important point is that we have here these lines indicating constant magnetic field ranging up to very highly magnetized objects, and at least a fraction of those could be very well result from the processes occurring at proton-neutron star formation. So there is indeed some motivation for considering magnetic fields in core collapse in supernovae. I'd like to go a little bit into the physics of the evolution equation for the magnetic field, which I've written down here, the induction equation. The time derivative of the magnetic field B is related to the curl of the electric field, for which we have here this expression. I'm mostly considering the first term, the ideal MHD term, whereas the second one involves the resistivity, which for most of the part of this talk will be ignored. In addition, we have the divergence constraint, which tells us that there are no magnetic monopoles. The magnetic field has to be divergence-free. This has important implications for the type of numerical codes we are using, but I won't go into those details either. The most important thing, however, is the different forces of the magnetic fields and the work plasma, a fluid, can do against those forces. There is, first of all, a magnetic field, which is an isotropic component, just the magnetic pressure, the half of B squared, a stronger field here indicated by these denser magnetic field lines, has a higher pressure and therefore exerts a force towards regions of weaker magnetic field. If the fluid, here indicated by these green arrows, compresses the magnetic field towards this region of higher pressure, it does work against the magnetic pressure and increases the magnetic energy until such time as the magnetic pressure is able to resist further compression. The second part of the magnetic force is an anisotropic one, which is the magnetic tension, which resists bending. If a fluid, like here, tries to bend a bundle of magnetic field lines, it has to work against this magnetic tension and therefore also increase the magnetic energy. So those two are the basic processes for amplifying the magnetic field, which, as we will see, play a role in core collapse. As I mentioned before, there is some motivation for considering magnetic fields, so I just add here these effects which the magnetic field can add to the supernova problem, and in particular those are turbulence and small-scale flows, and a certain contribution to pressure, as I've mentioned before. Those two effects can be coming from other sources as well. However, there are at least a few additional effects which are more or less produced best by magnetic fields and not so much by other effects. For example, large-scale angular momentum transport from, for example, a differentially rotating protoneutron star outwards to the post-shock region. There's also the possibility of generating large-scale structures by an inverse cascade in wave number space, and therefore a dynamo. And also we have one effect that has attained considerable attention, namely the magnetorotational instability, which in the end consists of runaway angular momentum transport. Within the framework of this presentation and our work, we are considering large-scale simulations, and for this I'm listing here the usual wish list. We have 4 such kind of simulations. We need to include hydrodynamics, the nuclear equation of state, relativistic gravity, and neutrinos, the latter being the most expensive part in terms of numerical costs. Here also, if you include magnetic field, it becomes even more important than it is usual to go from spherical to at least axisymmetry, and ideally 3-dimensional simulations. Also, a high numerical resolution can become very important, as we shall see later. Furthermore, you're opening up additional parameters in the pre-collapse state of the star. Usually you have metallicity, mass, and rotation, and further uncertainties of stellar evolution. Now we are, in addition, adding the unknown state or little constrained state of the magnetic field, for which 3D stellar evolution calculations would be very nice. So, on the other hand, there's a lot I'm not considering. For example, the effect of the magnetic field directly on the nuclear equation of state, or the interactions between neutrinos and matter. Also, effects such as crust superconductivity and superfluidity, which are going to play an important role in the longer phase as the proton-neutron star cools and transforms into an evolved neutron star. All of this will not be considered in the remainder of the talk. I'll start with the first amplification mechanism, which is just compression. If you recall my small transparency on the amplification effects, one of them was just working against magnetic pressure. This can be done by the radial infall during collapse. If you transform a magnetized sphere by compression to a much smaller radius, the magnetic field will grow. It grows roughly like rho to the power of 2/3. That is, if you go from the pre-collapse density of around 10 to 9 or 10 to 10 grams per cubic centimeter to that of a proton-neutron star in excess of 10 to 14 grams per cubic centimeter, you amplify the field by a factor of several hundred or thousand in strength. This could go as far as, for example, if the magnetic field reaches the energy density of the magnetic field reaches the energy density of the infall, which is never going to happen in realistic situations because the infall is supersonic, is far too energetic. But on the other hand, this amplification by 2 or 3 orders of magnitudes occurs in every collapse. And it also continues after the formation of the proton-neutron star in the core bounds, because matter is still going to fall onto the proton-neutron star. Just to show you a few numerical results, here are profiles of the field strength as a function of enclosed mass from 0 to about 2.5 solar masses for different times during collapse. This is the log of the magnetic field strength. We start off here, for example, in this black line at a central value of 10 to 10 Gauss. As the matter collapses, the field strength increases in this case by about a factor of 2,000 to a little more than 10 to 13 Gauss in the center at the formation of the proton-neutron star, which happens in this red line. So this is going to play a role in every single collapse. Further effects that occur afterwards, it should be noted here that this is a fairly simple effect. It doesn't change, in particular, the topology of the magnetic field. The ones I'm going to show you now do change the geometry quite a lot because they involve small-scale motions of this bending type, where you bend and twist the magnetic field lines. What I show you here are this is the contrast of the electron fraction in color scale, but the important point, the different colors indicate also non-radial motions. This is a zoom onto the proton-neutron star at 4 different times in a 2-dimensional simulation. The important point for our purpose here are these black lines, the magnetic field lines. As you see, these follow more or less the patterns of high and lower electron fraction that were created by non-radial motions. In this case, convection in the proton-neutron star. The proton-neutron star here has a size of around 50 kilometers in the first snapshot and contracts slowly to 30 and 20 something kilometers towards the end. And during all this time, we have convection operating between a radius of around 10 kilometers and the surface of the proton-neutron star. And the convection twists the magnetic field lines and increases the field strength. Also, towards the end of this process, we here observe a quite peculiar formation of a shielding layer of lateral magnetic field. Here you can see these flux tubes that are more or less at constant radius. Those are the product partially of what's going on in the convective layer below and magnetic flux, which is added by accretion from the outside. During all of these processes, you add additional energy to the magnetic field. It is, however, at least for this particular model, a simulation of a fairly weakly magnetized progenitor, never going to become large enough, strong enough to suppress convection entirely. But nevertheless, in terms of the final field strength, this more or less corresponds to a usual neutron star of, say, 10 to 12 Gauss field. However, so far, the magnetic field is not showing any, say, large-scale dipolar structure, but this relatively small-scale structure in the interior and this lateral layer on the outside. Now, this was the action of non-spherical flows in the protoneutron star. Now we are zooming out to larger dimensions. These are here simulations done a couple of years ago by the Oak Ridge group. The size here, this arrow, is 100 kilometers. So the excised black region is the protoneutron star, which I've showed you before. As you can see here, the color scale corresponds to the log of the magnetic field strength, as does here this volume rendering. The same or a similar type of non-radial flows amplifies the magnetic field also here behind the shock wave, which is this black surface here, and which, due to the non-radial flows, can become very aspherical, and which plays an important role in the generation of the supernova. But most importantly, in all of these flows here, by the way, the shock wave would be white, the white surface. In all of these models, the magnetic field has a very turbulent and small-scale structure. This is the same physics in a different simulation we performed a few years ago. A time sequence starting here. This is the first snapshot of this time sequence. You see here, a protoneutron star would be inside here, the first few tens of kilometers. These non-radial flows amplify the magnetic field in the surroundings of the protoneutron star and play an important role in some of the processes which leads to the development of an explosion. But only if, in this case at least, only if the magnetic field is initially already quite strong, which was not the case for this model, but for that one. The final state shown here is an expanding shock wave. If you compare this and that model, you see here that the structures here, these filaments, flux tubes, are much thicker in this case. Also in the protoneutron star, we have much thicker structures, which is the consequence of a stronger initial magnetic field. The stronger field means that the small-scale velocity field is less able to bend the magnetic field lines because it has to exert a larger force against the magnetic stresses. Therefore, some of these small-scale motions in all of these layers are suppressed by the strong magnetic fields, which in the end leads to the formation of larger high entropy. This variable here is entropy. Bubbles behind the shock wave, which then play an important role in the development of a successful explosion. Well, there's another amplification mechanism, which has been discussed a few years ago by Jérôme Guillet, namely the amplification of Alfvén waves traveling along field lines from here, the surface of the protoneutron star, outwards towards the shock wave. These, if we have a magnetic field line connecting the interior, the protoneutron star, to the shock wave, Alfvén waves may travel along the field lines and finally dissipate some of the matter here. During this process, as they arrive at the shock wave, they may be amplified by a certain amount, which was estimated here by Jérôme. However, our simulations show that this is not a very important process, because this amplification is only significant if the magnetic field is already fairly intense to begin with. But, okay. We're now coming to a much richer landscape of field amplification mechanisms. The results before were without rotation. If we, on the other hand, turn on magnetic fields, there's an important effect, namely, even if you start with a rigidly rotating pre-collapse core, first of all, the collapse will increase the rotation rate due to the conservation of angular momentum, but also it will, for the same reason, generate differential rotation from rigid rotation. And differential rotation can wind up a toroidal, radial, or theta component of the magnetic field into a poloidal one, a phi component. And this will, first of all, increase the total field strength and also enable angular momentum transport. And if the magnetic field becomes strong enough, this may even lead to the formation of jets and MHD-driven explosions. And under certain circumstances, which I'll explain in a little while, the magnetorotational instability can act in addition to this winding of field lines. The winding is a linear process. The magnetorotational instability, on the other hand, can amplify the magnetic field exponentially. And signatures of the MRI, as we'll see later, are these sheet-like structures which Pablo Cerda has seen in simulations a couple of years ago, the so-called channel modes. This is a time sequence of the magnetic strength, essentially magnetic strength as we go here, and this is the protoneutron star surface. And over a very short period of time, you form these so-called MRI channel modes. We'll see them a little later. We are not the only ones to have seen those. For example, the Moscow group has simulations which also show a rise, an exponential rise of the magnetic energy due to the same effect as also the groups in Japan. And very impressively, recently also the Caltech group around Philip Möster, who have even found indications of a magnetorotational dynamo and very beautiful magnetorotational explosions here. Just the magnetorotational instability can be understood as an instability of the Alfvén and slow mode of MHD. So this is a problem numerically, because essentially we need to resolve a wavelength of the slow Alfvén wave. And this wavelength is proportional to the initial magnetic field. So if you start from a relatively weak initial magnetic field, you need to resolve a very fine length scale. And this means that in most of these simulations, you start from an already quite strong magnetic field. So essentially, you don't need very much amplification by the magnetorotational instability. If you start from something which has a weak magnetic field, and you want to understand if this weak magnetic field can be amplified to very strong fields like those here, then you have a numerical problem. You want to resolve length scales which you cannot reasonably fit onto your computational grid. And, well, I'm going to skip this for now. Therefore, we took a somewhat different approach in several studies we performed during the last couple of years. Most recently together with Tomek Rembiasz in Valencia. Namely, we focused on small patches of the protoneutron star, representative subvolumes of not tens and hundreds of kilometers, but just about 1 kilometer. We switched off all the important and interesting physics of neutrinos and just considered magnetohydrodynamics in small boxes, but with a very high resolution down to several meters and even better in some cases. That means we can really follow the evolution of this, of the magnetorotational instability starting from much weaker initial fields. And this is what you get. Here we're showing as a function of time in milliseconds, so roughly 10 milliseconds, the evolution of the magnetic, essentially the energy contained in, or the stress is contained in one of those magnetic MRI channel modes. You see here an exponential growth over several orders of magnitudes. And this is our snapshots starting from here, this quite early time and to later times. This is a first 2D. I'm going to present you first 2D results. During this exponential rising phase, the magnetorotational instability develops these channel modes. Different red and blue colors correspond to opposite magnetic polarity. So we have anti-parallel magnetic fields. And as the MRI grows, this pattern doesn't change any, but only increase in its intensity. After some time here, the growth stops, and this pattern is disrupted by secondary instabilities. And the important question in this context, now to understand how far the magnetic field can grow, is at what point this disruption occurs. 2D is not enough for this purpose, but you have to go to 3D. And if you do so, you can rely on work done in 2010 by Martin Pessa, who studied these perturbations that lead to the growth of these secondary instabilities. And in particular, the most important ones, Kelvin-Helmholtz modes. Kelvin-Helmholtz modes, which develop because you have here antiparallel flows, or tearing modes, which develop because you have antiparallel magnetic fields. So those two types grow exponentially with a growth rate that depends on the strength of the MRI. So they grow. The MRI grows at a constant rate during all of these 10 milliseconds, but these parasites grow very slowly here because BMRI is weak. They grow very rapidly here because BMRI has grown by several orders of magnitude. And as a consequence, at some point, these secondary instabilities grow faster than the primary instability, and at this point we have exactly what's shown here, namely the disruption of the magnetorotational instability of the channel modes, and then growth stops. This is actually completely wrong, because the instability we see here are channel modes, tearing modes, consisting of magnetic reconnection. O points and X points, the field lines would look something like that. And this is completely artificial due to the axisymmetric geometry. In axis symmetry, Kelvin-Helmholtz modes are mostly suppressed. However, in 3D, they grow faster then the tearing modes. And this is the same as before, just in 3D. The snapshots before were basically slides here, like this one on the front. And now we're showing you the same as before, radial magnetic field strength. Early on, the picture looks as before, these anti-parallel radial fields. And now here at disruption, the field structure looks very different from before, which is the consequence of now Kelvin-Helmholtz instabilities rather than tearing modes disrupting the channel modes. So as Tomek showed a few years ago, in 3D you get these very nice Kelvin-Helmholtz modes. This leads to a somewhat earlier disruption of the growth of the channel modes, and therefore modifies the onset of the turbulent phase, which afterwards would continue more or less oscillating around this value for many, many more time. Again, the same in a 3D plot. You see here the pattern of Kelvin-Helmholtz modes, Kelvin-Helmholtz rolls, which this would be, by the way, rotation direction. This is radius, and the direction outwards is the vertical direction. And this is what I showed you before, growth of the magnetorotational instability and the growth of several modes of these parasitic instabilities. First growing very slowly, and as the MRI continues to grow at the same rate and BMRI is increasing, these parasitic instabilities grow faster, and until they reach the same magnitude as the magnetorotational instability, at which point they disrupt the MRI. So I'm going to skip the rest and just, actually, just to mention this, we did later on simulations of the core collapse in axisymmetry for several different progenitors here of a high mass of 35 solar masses, rotation, and different magnetic fields, and they show all this spectrum of different evolutionary paths I mentioned before. For example, explosions driven by neutrinos and hydrodynamic instabilities, but as well magnetorotational jets, in which case also we see indications of the magnetorotational instability in the proton-neutron star, which would be at the center here. And that is basically it. So I'm going to summarize the talk for you. The magnetic field is certainly present in most core collapses. It may or may not play a role depending on the initial conditions, and also on the prospects of magnetic field amplification, for which we have a few processes which are supposed to work in every case, like the compression, but others which depend more strongly on the physics of the progenitor and the possible processes inside the collapsing core, like, for example, the development of the magnetorotational instability. So thank you very much for your attention.
Thank you, Martin. Time for 2 quick questions, perhaps.
Can you say something about the initial inclination angles of neutron stars?
Well, something, but not very much, honestly, because the process, we can simulate these models only for say 1 or 2 seconds. The magnetic field of the neutron star is certainly influenced a lot by processes that go on over a longer time, in particular the formation of the crust, which probably takes place at 1 minute or more after formation. So we have to wait for much longer time, during which still processes like potentially accretion, but also convection inside the protoneutron star plays a role. But so far, what we see is mostly a small-scale field, no prominent dipole.
Thank you, Martin. One more question.
Are there any attempts to consider influence of magnetic field on electron capture supernova explosion, or what do you think, how important it might be?
On the explosion process itself, probably not that much, because those, as we saw in simulations started for 12 years ago, or even more, by Francisco Xuquitaura, explode very easily, even without additional ingredients. So probably you don't need a lot of magnetic field there to help the explosion itself. Of course, the protoneutron star may still develop any kind of, say, dynamo.
Thanks, Martin. So it's time to move on to another speaker, who is, let's thank Martin. So the next